Hello everyone, and welcome to another one of my videos on organic chemistry. The topic of this video is addition reactions. More specifically, why is it in some addition reactions there are two organic products, but in others there's only a single organic product? First of all, on the screen there's a generic explanation about what addition reactions will involve. It requires a alkene functional group, so carbon-carbon double bond, and that is going to react with some sort of small molecule such as H2, Cl2, HCl or HBr or H2O. During the course of the reaction, the double bond will break to leave a single bond, and if I use the water molecule as an example for this, the water molecule is also going to break into two pieces with three atoms. That leaves you an H and an OH as the two pieces, and each one of those pieces will bond to one of the carbon atoms that was originally in the double bond. An important thing to consider for this is that when it comes to how this is achieved, there is no above or below the double bond in terms of this reaction, so it makes no difference if I was to put the OH and OH on that side or the H and OH on that side, simply because once it is attached and I have a single bonded carbon structure, there is no above and below because the whole molecule can twist. So above and below is not a relevant idea when it comes to addition in straight chain alkenes. In order to get two products in these reactions, there are two rules that must be satisfied. The first rule is that the alkene must be asymmetric. This essentially means that the left and right sides can't be mirror images of each other, or I guess we could say the carbons in a double bond can't have the exact same groups as each other. This is different from the requirements for geometric isomers, and that's often a source of confusion. We're not interested in whether or not the two groups on each carbon are different to each other. We're comparing the left side as a whole, what groups does it have, to the right side as a whole, and what groups does it have. The red structure would not be an asymmetric alkene, simply because both of those two carbons have an H and a CH3 attached to them. The green structure will satisfy this rule because an H and a CH3 is different from having two H's. The second rule is that we must be adding two different atoms or groups of atoms to these two carbons in the double bond in the first place. So that means that adding reacting H2, Cl2 or Br2, it is not going to be possible for there to be two products, simply because we're adding an H both sides, a Cl both sides, or a Br both sides. The options in green, however, will satisfy this rule because we're either adding an H and a Br, an H and a Cl, or an H and an OH. So there's different things that are going to be attached to the left and the right carbons. Let's have a look at a example, perhaps. I have but2ene here. I've actually got the cis isomers, but that is actually more or less irrelevant for this reaction. The cis and trans isomers will react the same way, and really it's irrelevant which one I start with. If it reacts with water, there is two ways I can add the water molecule onto but2ene, which is why I have two structures. Remember that above and below is irrelevant, so there's no point me asking how do these two reactions end up being different, because either way the OH both goes to the left side in each case. What I'm interested in, how is it different if the OH goes to either the left side or the right side? So during the reaction, double bond will be broken. The OH in this case can go to the first carbon, well, the carbon on the left of that double bond, and then in this case here, double bond breaks, Now the H goes to my left carbon and OH goes to the right. In terms of structures I've got here, initially, even though I was adding two different atoms or groups across the double bond, butene was actually a symmetrical alkene, so I will not have two different products in this case. And hopefully this will illustrate it, because if I've got a alcohol on the second carbon in a 4-carbon straight chain, I've got the exact same thing over here, it's just that this is now carbon 1 on the right side. And if I in fact move the molecule over, maybe do a slight adjustment to make it line up in terms of how the carbons sit in a straight line, I have essentially got the exact same molecule. There is only one product from this because the original alkene was symmetrical. It did not matter which carbon in the double bond received the OH. Either way around, I still get the OH attached to the second carbon on the chain. There is only one product possible from this reaction. Now, if I just quickly restore some structures and try out a asymmetrical alkene, which will be propene. I now have propene. It is asymmetrical because in terms of this side versus that side, there are different groups on each side. We're either dealing with two H's and an H and a CH3, so they're different from each other. The water molecule could be added really in either way around. Either the OH will go to the left or the OH will go to the right. If the bonds are broken, products are formed. We should find that there's actually going to be two different products from this reaction. The first one involves OH going on the very end of the chain. We'll be dealing with their propane 1-ol or 1-propanol. And then in the second one, the OH will actually go to the middle because the H goes to the one on the end of the chain. And I now have propane 2-ol or 2-propanol. We end up with two different organic products in this case because we either have the OH bonded to the middle carbon or the carbon on the end of the chain. The lack of symmetry in the original propene reactant meant that the two original carbons in a double bond weren't equivalent to each other. We get a different product depending on which one gains the H or the OH. This is another example just on paper. I should have actually, for consistency, made these a green structure because we do get two products, which was the color coding I was using earlier. But the left carbon in this case has two methyls attached. The right-hand carbon has a hydrogen and a methyl attached. So they are different from each other. There's no mirror plane between those two. It is an asymmetrical alkene, which means I can either add when I add the OH to the left side of that double bond or to the right side, I end up with different structures. It's not a case of the OH being on the end of the chain or the middle of the chain, but I either get the OH attached to the same carbon with the side chain, or I get the OH attached to the other carbon which does not have a side chain attached to it. Either way, they have different structures. They are two different products. Once again, an asymmetrical alkane has given us two organic products. Hopefully that was a fairly sort of brief video, maybe cleared up some misconceptions about that, and thanks for listening and watching.